the optical counterpart of a radio source designated 3C273. It looked, to every other astronomer who had examined it, like an unremarkable star. Schmidt analyzed its spectrum and felt the ground shift beneath him. The spectral lines were shifted so dramatically toward the red end of the spectrum that the object had to be approximately 2.4 billion light-years away. For a point of light visible to a ground-based telescope at that distance, it had to be producing more energy than an entire galaxy of hundreds of billions of stars, from a region of space no larger than our solar system. The class of objects Schmidt had identified, quasi-stellar objects, or quasars, turned out to be the most energetic sustained phenomena in the observable universe. They are powered by supermassive black holes, actively consuming surrounding material, drawing in gas and dust and stars at such enormous rates that the infalling matter heats to millions of degrees, and radiates across every wavelength, outshining everything else in their host galaxies by factors of hundreds or thousands. They are not rare. Astronomers have cataloged over 1 million of them, scattered across the observable universe, most of them burning brightest in the distant past, when the universe was young and gas was abundant. In February 2024, a team led by Christopher Wolfe published results in Nature Astronomy, confirming that a quasar designated J05294351 is the most luminous object ever measured, with a brightness approximately 500 trillion times that of the Sun. The black hole powering it consumes the equivalent of 1 solar mass every single day. Its light, currently reaching our telescopes, left the object when the universe was roughly 1.5 billion years old. We are seeing something that existed in a universe radically different from the one we inhabit now. And even by that universe's extraordinary standards, it was exceptional. Quasars do not merely shine, they reshape the cosmos around them. The jets they launch, beams of magnetized plasma accelerated to near the speed of light, can extend for millions of light years into the surrounding intergalactic medium, injecting energy equivalent to trillions of supernovae into the gas that would otherwise collapse to form new galaxies. This process, quasar feedback, is now understood to be one of the primary mechanisms by which the universe regulates star formation across cosmic time. The violence happening in the cores of these objects is not local. It echoes across the entire intergalactic environment. The most powerful engines in the universe have been actively rewriting the intergalactic medium for billions of years, determining where galaxies could form and where they could not, heating the cosmic web, launching jets millions of light years long, and we still do not have a complete physical explanation for how a black hole generates and sustains those jets. The object that Schmidt found hiding in plain sight as a dim star has turned out to be a force that shaped the universe you live in. Number 3. The Hercules Corona Borealis Great Wall. In 2013, astronomers Istvan Horvath, John Hakala, and Zsolt Bagoli were mapping the distribution of gamma-ray bursts across the sky, using these extraordinarily powerful explosions as tracers of where matter concentrates in the distant universe. Gamma-ray bursts are visible across billions of light years and mark the locations of massive stars collapsing or neutron stars merging, making them useful probes of large-scale structure. What the team found in a region of sky spanning the constellations Hercules and Corona Borealis, published in Astronomy and Astrophysics in 2014, was a clustering of bursts so pronounced and so vast that it violated one of the most fundamental assumptions of modern cosmology. That assumption is called the cosmological principle. The idea that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations. It is not a minor working assumption. It is the foundational premise on which virtually all of modern cosmological modeling rests. Without it, the equations that describe the expansion of the universe, the formation of structure, and the behavior of dark energy become dramatically more complex, possibly intractable. The cosmological principle sets a theoretical upper limit on how large any structure in the universe can be, approximately 1.2 billion light-years, beyond which the universe simply should not show coherent organization. The Hercules Corona Borealis Great Wall is estimated to span approximately 10 billion light-years. That is not a rounding error. It is roughly 1/9 the diameter of the entire observable universe. A structure of this scale requires not only matter to be arranged over extraordinary distances, but time for gravity to have assembled that arrangement. The universe has existed for 13.8 billion years. There has not been enough time, by standard physics, for anything 10 billion light years across to have organized itself into a coherent structure. And yet the clustering is there. The finding is debated, and that debate is important to acknowledge. The structure is identified through a statistical excess of gamma-ray bursts, not through direct imaging of the galaxies themselves. Some cosmologists argue the clustering may reflect observational bias or an insufficient sample. Others have attempted to confirm the structure through independent methods with mixed results. It has not been formally accepted as a definitive physical structure by the full cosmological community, and it has not been dismissed either. It persists in the literature as a serious and unresolved anomaly. If the Hercules Corona Borealis Great Wall is real, it does not merely challenge the cosmological principle, it breaks it. And a universe that breaks its own foundational rule at sufficient scale is a universe whose governing equations may need to be rewritten from the ground up. The most disturbing possibility is not that we found something big. It is that we found something that should not exist, and we cannot yet say with certainty that it does not. Number 2, the axis of evil. In 2003, the WMAP satellite delivered what was supposed to be the definitive map of the cosmic microwave background, the ancient light from 380,000 years after the Big Bang, a snapshot of the infant universe encoding the seeds of all structure to come. Cosmologists expected to find a map consistent with isotropy, a universe with no preferred direction, no special axis, no orientation, its fluctuations scattered randomly across the sky. In 2005, Kate Land and João Magajo of Imperial College London published a paper in Physical Review Letters announcing what they called, with deliberate provocation, the axis of evil. The largest features of the CMB, its quadrupole and octopole moments, the broadest temperature patterns visible across the whole sky, were aligned with each other, and aligned with the plane of Earth's orbit around the Sun. The cosmological principle demands that the universe look the same from everywhere, that no location and no direction be special. Our solar system is an infinitesimally small speck in an ordinary galaxy in an ordinary region of space. There is no physical reason, under any standard model, why the largest structures in the observable universe should show any relationship to the plane of our planet's orbit. The probability of such an alignment occurring by chance was estimated at less than 1%. It was, and remains, deeply strange. The anomaly was not a WMAP artifact. The Planck satellite, a more sophisticated instrument operated by the European Space Agency, released its CMB maps in 2013, 2015, and 2018, each time with improved sensitivity and refined foreground removal. The axis of evil was still there. Every major systematic error that could plausibly explain it has been investigated and found insufficient. The alignment of the CMB's largest scale features with the ecliptic plane has survived more than 2 decades of scrutiny and has not gone away. Proposed explanations range from the mundane to the extraordinary. Some researchers suspect residual foreground contamination from local structures in our galaxy or solar system. Others have suggested the universe may have a non-trivial topology, a specific shape, perhaps a finite torus or a more exotic geometry, that would impose a preferred direction on the CMB. A small number of theorists have proposed it as evidence for anisotropic cosmological models, universes that are not the same in all directions at the fundamental level. None of these explanations has achieved consensus. What has been written into the oldest light in the observable universe at the very largest scales we can measure appears to know where we are. That is not supposed to be possible. And the fact that it persists, confirmed and reconfirmed across 2 generations of satellite observations, unchanged by every attempt to explain it away, means that whatever lies between and beyond the galaxies of our cosmos may be organized in ways our current physics cannot yet describe. What comes next on this list is even more fundamental because, unlike the axis of evil, which might eventually be explained by something exotic but local, number 1 is a force operating everywhere in the universe right now, and we have no idea what it is. Number 1, dark energy. In 1998, 2 independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. The expectation was unambiguous. The Big Bang had sent matter flying outward, and gravity, the universal attraction of everything for everything else, was breaking that expansion. The only question was whether gravity would eventually halt the expansion and reverse it into a big crunch, or whether the universe would expand forever but at an ever-decreasing rate. Both teams used Type Ia supernovae as standard candles, explosions of such consistent intrinsic brightness that their apparent faintness revealed their distance with precision. Saul Perlmutter's Supernova Cosmology Project and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, collected their data independently, ran their analyses independently, and arrived at the same answer. The expansion was not slowing, it was accelerating. Something was pushing the universe apart with increasing force, and it was winning against gravity across every distance scale large enough to matter. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. The thing they found was named dark energy, and it has refused to be understood ever since. Dark energy constitutes approximately 68% of the total energy content of the universe, confirmed to that precision by the Planck Satellite Collaboration's 2018 results. Ordinary matter, everything made of atoms, every star, planet, gas cloud, and living thing, accounts for roughly 5%. Dark matter accounts for 27%. The majority of everything that exists and drives the behavior of the cosmos is something we cannot detect, cannot interact with, and cannot explain. It does not clump. It does not form structures. It appears perfectly smooth, uniform, filling all of space with constant density, exerting its repulsive effect equally everywhere. The leading theoretical candidate for dark energy is vacuum energy, the energy of empty space itself, represented in Einstein's equations by the cosmological constant he famously introduced and then abandoned. When theoretical physicists calculate what the energy density of the vacuum should be from first principles using quantum field theory, they obtain a number. When they compare that number to the observed value of dark energy, the discrepancy is 10 to the power of 120. That is a 1 followed by 120 zeros. It is described without hyperbole as the worst prediction in the history of physics. Our deepest theory of matter and energy, quantum field theory, and our best theory of gravity, general relativity, do not merely disagree on dark energy. They disagree by the largest margin ever recorded between a theoretical prediction and an observation. Alternative theories have multiplied in the absence of a solution. Quintessence proposes that dark energy is not a constant, but a dynamical field, one that changes over time and varies across space. Modified gravity theories suggest that Einstein's equations break down at cosmological scales and need to be replaced by something more general. The Hubble tension, the persistent disagreement between different methods of measuring the universe's expansion rate, has led some cosmologists to propose that dark energy's behavior is evolving, that it may have been different in the early universe than it is today. None of these proposals has been confirmed. New data from the Dark Energy Spectroscopic Instrument and the Euclid satellite are actively testing some of them, but no resolution has emerged. Dark energy's effects are exclusively intergalactic. Within galaxies and within galaxy clusters, gravity still dominates, holding structures together. But in the vast spaces between galaxy clusters, dark energy is winning, pushing the universe apart faster than it was yesterday, faster than it was 1 billion years ago, and slower than it will be 1 billion years from now. Galaxies beyond our local group are already accelerating away from us. Given enough time, they will cross our cosmic horizon and vanish, unreachable and unobservable forever. The universe is not merely expanding. It is being systematically disassembled, structure by structure, by a force that constitutes 68% of everything and that we cannot explain with a single confirmed equation. We do not know what dark energy is. We cannot detect it directly. We cannot stop it. And every second that passes, it has already won a little more of the universe than it had before. If you want to see more videos like this, click the video on screen now and make sure to subscribe.